Chapter 3.1, Exponential Functions. So here we're starting a new unit, new chapter. We'll be looking into first some stuff that hopefully you remember from your studies of algebra. But if you don't, there is a review of exponential rules, etc. that I really recommend you looking at before going into this video. So make sure you're familiar with your general exponent rules because those are going to be very helpful in understanding exponential functions. Without further ado, essentially we want to look at first our definition of what is an exponential function. An exponential function defined as f of x equal to a b to the x with a few stipulations. A cannot equal 0 because then we just have f of x equals 0 and that's not very helpful. B has to be greater than 0. This is because if we have a negative base to an exponent, things get a little bit weird when we're working with functions. Especially because we can't take the square root of a negative number. We can't, etc. Like there's a lot of problems that would occur there. So we just say, okay, b is greater than 0 to solve any problems like that. And b cannot equal 1 because 1 to any power is just 1, and so it tends to not look in the way other exponential functions look. So, a b to the x. B is our base. A is called our initial value, so where our function begins at x equals 0. And x is, of course, the exponent. So the difference between this and a polynomial is that x has to be in the exponent. There's no x's outside the exponent. This isn't like x squared, even though it feels like it's similarly structured because x squared versus b to the x, it's still something with an exponent, right? But here, the x is in the exponent. That's the important part. That fundamentally changes what these functions look like. So in this case, for the graph shown, we have f of x equals 1 times 2 to the x. 1 is the initial value, so we can see there's this point here at 0, 1. So this 1 is the initial value. It's what happens when when x equals 0. 2 is the base, so it's the thing that is being exponentiated, and x is the exponent. The domain of any exponential function is always all real numbers because there's no problem with plugging in any number into this exponent right here, right? There's nothing that I couldn't plug in. However, the range isn't quite so simple. So the range is based on whether or not a is positive or negative. So if a is positive, we have a function that looks generally like the picture of 1 times 2 to the x. The range goes from 0 to infinity. If a is negative, however, our graph is going to flip over the x-axis. If you remember rules about transformations, those are going to come up soon. And so it will look more like this, which means that the range would be from negative infinity to 0. The y-intercept will always be at 0a, so 0, the initial value. That's where the phrase initial comes from because it's time 0, or when we begin at 0, so initial. Here's where things get a little bit interesting, is that an exponential function always has a horizontal asymptote. Specifically, the basic exponential, like so, has a horizontal asymptote at y equal to 0. So we can see that we can see kind of what's happening here as our function is approaching the x-axis. It doesn't appear like it's crossing. It looks like it's just getting smaller and smaller, and that's true. That's what's going to happen. Because if you think about it, looking at this function here, I can take 2 to a negative power. And again, I'm hoping you've reviewed your exponent rules and you remember what it means to take a number to a negative power. So 2 to the negative 1 equals 1/2. 2 to the negative 2 equals 1 over 2 squared, so 1/4. 2 to the negative 3 equals 1 over 2 cubed, or 1/8, and so on. So we are staying above 0. All of these numbers are positive, but notice that they're getting smaller and smaller as I get more and more negative input values. So if I have 2 to the negative 1,000, it's going to be very, very, very small, but it's still going to be above 0. There is no way for this to ever equal 0. So we have this, so that's where the range comes from, that we're starting at 0, but we never include 0. Notice that this is not including 0. And we get this horizontal asymptote that as x goes towards negative infinity, so remember our arrow notation, as x heads towards negative infinity, f of x goes towards 0. But this isn't true in the positive direction. We have a horizontal asymptote, finally, that's only really true in one direction, and that's okay. Remember when I introduced the idea of horizontal asymptotes when we talked about rational functions, that you can have up to 2 horizontal asymptotes, one for going towards negative infinity, one for going towards positive infinity. With rational functions, we only ever saw it where it's the same in either direction. We never really thought about it. But for exponential functions, we have a horizontal asymptote that's only relevant in one direction. If we head towards positive infinity with our x, if we're going this way, f of x is just going upwards. So there is no asymptote in that direction. So we could say f of x goes towards positive infinity as well. Again, this is specifically for when a is positive, basically in this particular case. If a were negative, then it would look a little bit different, but the point is it's always going to have this horizontal asymptote at y equals 0 for this basic exponential function. If b is greater than 1, we have an increasing function. So here I have b, the base is 2, so it's an increasing function. But if b is between 0 and 1, we will actually have a decreasing function, because essentially it will look like the opposite situation, where it'll look something like this. Because, let's say this were, example, f of x equals 1 times 1/2 to the x. Well, 1/2 to the x, that's, as we've already sort of discovered, 2 to the negative 1, right? And again, remembering our exponent rules, this would be 1 times 2 to the negative x. So that negative x, that would be a transformation. Plugging in negative x flips us over the y-axis. That's why we're going in the opposite direction. So you can always think of having a negative exponent as being a fractional base instead. Those are interchangeable. Now let's look at a few examples. We want to see which of these are actually exponential functions based on our knowledge of exponentials now. So first, we'll look at 4 to the 3 times x minus 2. In this case, it's not structured like an exponential function yet, but we can use our exponent rules to manipulate this one. So 4 to the 3 times x minus 2 has multiplication in it. We have a few rules we can work with here. So anytime there is multiplication in our exponents, we can do the following. So multiplication, we can do 4 cubed times 4 cubed, let me try that again. 4 cubed to the power of x minus 2. That's an option. We could also distribute. So 4 to 3x minus 6. Either is an option for simplifying this. We're not done yet, though, but it's starting to look a little bit more like what we want in either option. So 4 cubed is going to be 64. So 64 to the x minus 2, getting closer. And minus 2. Again, we employ an exponent rule here. So this will be 64 to the x over 64 squared, or in other words, 1 over 64 squared times 64 to the x. All I'm doing is separating that fraction. And we can see this is our a, b, and then we have our exponent. If we had instead started from 4 to the 3x minus 6, we would have done this separation 4 to the 3x over 4 to the 6th, which equals, let's see, 4 to the 3x over 4 to the 6th. So that's going to be 1 over 4 to the 6th times 4 cubed to the x. Oh, that should say 4 to the 6th, not 46, so careful there. Which equals 1 over 4 to the 6th times 64 to the x. Once again, 4 to the 6th and 64 squared are the same number. If you check that in a calculator, you'll find that's the same number. So, works out either way. But the point is we have our a and we have our b. And there's more than one way we can get there. So you definitely need to make sure you're refreshing yourself on those exponent rules if none of what I just did made sense to you. Look back, look at that review that I've posted, make sure you understand them. Okay, next we have x cubed. X cubed has x as the base and 3 as the exponent. So this should be an automatic no, because we only want x in the exponent for an exponential. This is just a polynomial function, or more accurately, a power function, or a very simple polynomial. So it's not an exponential. Those two, you can't be both. It's one or the other. For 1/3 to the x, this one's already in the format we like. We just need to check, does b match the rules that we set for it? B is greater than 0, and it's not equal to 1. It's 1/3, so yep, we're good. But for j, it's in the same format, but we see that b is in fact less than 0 because it's -2. So that is not an exponential function. So we get 2 out of the 4 of these are exponential functions. One required a little bit more work than the others, but just to make sure you kind of understand how you can manipulate these things. All right, now let's look at how does exponential growth compare to linear growth. So here I have two functions, f of x equals 2 to the x, and g of x equals 2x. So 2 to the x is our exponential function, 2x is a linear function. You'll notice that they grow in a very different manner. So linear growth is defined by values repeatedly increasing or decreasing by the same amount over each equal increment. So we can see that we just add the same amount every time. We add 2, add 2, add 2, add 2, and so on. That's the pattern for linear growth. However, for exponential growth, values repeatedly increase or decrease by the same percentage, also known as the same relative amount, over each equal increment. So in other words, same multiple. So times 2, times 2, times 2, times 2. So of course, if we're multiplying by 2 repeatedly, we're going to get a much larger number as we grow than if I'm just adding 2. So where linear growth is a nice straight line, exponential growth ends up being a curve that speeds up as we head towards larger input values. So here we have just a table of what's happening when b is greater than 1. We can see that if x is -3, I get 1/8. -2, I get 1/4. -1, 1/2. 0, 1. 1, 2. 2, 4, 3, 8, and so on, right? I square 2, I cube 2, I take 2 to the 4th, 2 to the 5th, 2 to the 6th. These are going to be very large numbers as I go on, and it's getting a larger and larger increase. Notice that the increase from here to here is smaller than from here to here, which is smaller than from here to here, which is smaller than from here to here, which will be smaller than here to the next thing, and so on, because that's how exponentials work. Now, if b is less than 1, as I hinted at before, essentially well, 1/2 to the negative 3, that's a little bit hard to interpret, but let's just plug it in and see what happens. So negative 3. This would be 1/2, 1 over 1/2 cubed. Okay, well, do we really want to think about that necessarily? No, but we can figure out that's 1 over 1, 2 cubed, or in other words, it's going to be 2 cubed. There's a lot of ways to look at that. If you remember that a negative exponent with a fraction just sort of flips the fraction over, then you can immediately say that this is 2 cubed. If you want to apply the cube to both things individually, that's another way you can look at it. But the point is, we can also, of course, say, well, 1/2 to the negative 3 is equal to 2 to the negative 1 to the negative 3, which equals 2 cubed. Again, all these exponent rules, there's usually multiple ways you can do this manipulation. It's going to be up to you to determine which one's the one that makes the most sense to you. But the main takeaway is that 1/2 to the negative 3 power is 8. 1/2 to the negative 2 power will thus be 4. 1/2 to the negative 1 will be 2. We still have the same initial value, so I plug in 0. Anything to the 0 power is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4, 1/8, and so on. So we are decreasing instead. But it's still basically the same shape, it's just flipped over the y-axis. Now the last thing that we need to sort of define before we get to how do we really graph these functions is the base e. So this is a very important defined number for us. So often applied as well as theoretical problems use a particular irrational number that we call e. E stands for Euler's number. Euler, yes, does start with an E. It's the mathematician who studied the number. So E for Euler. But like pi, we can only approximate E numerically as about 2.7182818 and so on. It's an irrational number, just the same way pi is. But it has a specific definition in the same way that pi's definition comes from the circumference of a circle. So here, the definition, now, mind you, you're not meant to really understand what this means at this moment. This uses some notation that you'll learn if you go on to calculus. But e is equal to the limit as n approaches infinity of 1 plus 1 over n to the n power, which, to essentially attempt to explain this, means that if I take this function right here and look at what's happening as n goes towards infinity, so what's happening just like what happens when x goes towards infinity. If I increase n without bound, what does it approach? Does it have a horizontal asymptote? It does, in fact, have a horizontal asymptote. The horizontal asymptote occurs at e. So that's where this comes from. You are not meant to memorize this definition. You do not need to know what this notation necessarily means right now. That's all calculus stuff. All you need to know is E is about 2.718, but E is a button on your calculator. Use the E key on your calculator. Don't try to memorize E up to 100 digits or anything like that. Just use the E key on your calculator. Don't round or anything like that. So, knowing that E is 2.718, what would the graph of e to the x necessarily look like? Well, e is a positive base here. So positive base means, so that's good. It's not equal to 1, that's good. It's also specifically, it's greater than 1. So it's a base greater than 1 means it's going to look very similar to our 2 to the x did. To the way our 2 to the x did. So this is f of x equal to e to the x. Notice that it's got the same initial value at 0, 1, or the same y-intercept, etc., but it increases a bit faster than just 2 to the x does, etc. E to the negative x, on the other hand, well, as we know about our negative exponents, that's going to be equal to 1 over e to the x. So that's going to be one that's going this way, flipped over the y-axis, etc. Essentially, all you need to take away from here is what direction does e go in, generally what number is it, but use your e key on your calculator, and it shouldn't be too difficult. Just, I want you to be aware that e is not a variable. E has a very specific definition in the same way that pi has a very specific definition. So when you see it, don't try to plug in for it, just leave it as e. E is a number. We wouldn't plug in for pi, don't plug in for e. Use the exact value that you can find, the key on your calculator, or leave things in terms of e. That's what we want. All right, so graphing. So an exponential function with the form f of x equals b to the x. So notice this is the most basic form that we can make. With b greater than 0 and b not equal to 1, has the following characteristics. It is a one-to-one function, right? That means it passes the horizontal line test, and of course it passes the vertical line test. It's a function in the first place. It has a horizontal asymptote at y equals 0. Its domain is negative infinity to positive infinity. Its range is 0 to infinity. Its y-intercept by default is 0, 1. Remember, before I said, its y-intercept is 0a, but right here we're looking at the most basic form that doesn't even have an a, okay? So a is 1 in the basic form. So its y-intercept is 0, 1. It's increasing if b is greater than 1. It's decreasing if b is less than 1. All right, so all of that, not new information. That's stuff from the first slide. What's going to be new is now let's apply transformations to it. And when I say that's new, I mean it's really just taking some old stuff that we went over multiple times, but mostly in chapter 1.6, and applying it to our new type of function, our exponential. So, for any constants c and d, the function b to the x minus c plus d will shift vertically by d units up and horizontally by c units to the right. So we can see that g of x equals 2 to the x plus 3, shifts us up by 3. 2 to the x minus 3 shifts us down by 3. Here, 2 to the x plus 3 shifts us to the left by 3. 2 to the x minus 3 shifts us to the right by 3, making sure that we're paying attention to whether we're in the exponent or not, because I realize how I said that out loud, not super helpful, but you have to be very careful, because it's not always super clear in these cases. So you want to make sure your vertical shifts are when you are adding or subtracting something outside of the exponent, right? It's the d part of this. Whereas your horizontal shifts are adding or subtracting something inside the exponent, so up in the exponent. That's when we shift left to right. So, what does this change about our function? Essentially, it changes first the y-intercept, which will be still at 0, of course, but the y value will be b to the negative c plus d. So remember, on our basic function, b to the negative c plus d, well, d is 0, and c is also 0. B to the 0 is 1, because anything to the 0 power is 1. So we get 0, 1 on our basic function. But as soon as we are shifting it around, it's going to change. Next, its horizontal asymptote will change. The horizontal asymptote is shifted by d. So it's normally at 0, it's now at 3 or negative 3, shifted up or down. The only time in any of these transformations that the horizontal asymptote changes is if we are adding something or subtracting something outside of the function. Otherwise, the horizontal asymptote stays at y equals 0. The range comes from the horizontal asymptote. So the range in this case would be d to infinity. Or if we're flipped over or something like that, and later we'll see, it can be on the negative side of that. But for our basic, just positive, our basic b to the x minus c plus d, where we're not multiplied by any negatives or anything like that, range is d to infinity. But the domain remains unchanged. Next, we have stretches and compression. So this is where we bring in that a, that change to our initial value. So if we are stretched vertically by a factor of a if a is greater than 1, and we are compressed vertically by a factor of a if a is less than 1. If the absolute value is less than 1, I should say. So if we, in this case, see it's 3 times 2 to the x, so that vertical stretch, remember vertical means up and down, so we can see that the whole function seems to be pulled upward by a multiple. So every piece is pulled up by a different amount, which is different than we saw here, where the entire thing is shifted up by the same amount. Notice that all of my arrows are approximately the same length when I do this shift. Whereas for a stretch, it's a multiple. The arrows should be different lengths because I'm taking whatever this y value is and multiplying it by 3 in this case. Here, the compression in the same way is taking each value and multiplying it by a fractional amount. So if I have 6 or something like that, I'm dividing it by 3 to go down to this smaller number. So the arrows, once again, are different amounts because it's going to be relative to whatever the original y amount was. So that's how stretches and compressions work. Hopefully we remember this again from chapter 1.6, but if you're rusty on it, please go back and look at that chapter. It'll help here. So what fundamentally does this change? Basically, the only thing that is going to really change about your graph when you do a stretch is where the y-intercept occurs. So y-intercept will occur at 0a. Now this is, of course, a situation where we do not have any vertical and horizontal shifts to affect the y-intercept. So just the plane AB to the x, the y-intercept is at 0a. Next we have, well, what if a were negative? So here is just, if I put a negative out front of b to the x, what happens? That's an x-axis reflection. So if a is negative, then we're getting the stretch and the reflection, essentially, if we have some a that's not 1. So x-axis reflection, we get everything just flips over. So what changes is the y-intercept will become 0, negative 1. The domain unchanged, but the range is negative infinity to 0 now. Because we are on the other side of our x-axis. But the horizontal asymptote still remains at y equals 0. Similarly, if I have b to the negative x, as I've sort of hinted at already, this is a y-axis reflection. So this is the same as saying 1 over b to the x. Those are the same thing. So it's going to flip us over the y-axis, which basically doesn't change any of the fundamental facts about it, except that it's decreasing now. So y-intercept is still going to be the same, domain, range, horizontal asymptote, all of those remain unchanged. But the direction we're facing will be different. So you still have to pay attention. It's not like it's the same graph, it's just that those fundamental facts aren't going to change. All right, so now that we know all of that, let's look at taking a function that we know how to graph, hopefully, and applying all of these transformations to it and figuring out what should the final function be. So here I have f of x equals e to the x. We want to vertically stretch it by a factor of 2, reflect it across the y-axis, shift it left 1 unit, and shift it up 4 units. Remember to apply horizontal reflections to our shifts when we write out this function. So I'm going to start with f of x equals e to the x as my base function. I'm going to apply my reflection about the y-axis first. So that's just adding in this negative to my x. Then I'm going to apply my shift left by 1 unit, remembering again to apply the horizontal reflection to the shift. So that means that I'm really putting this negative outside of x plus 1. Then I am going to vertically stretch by a factor of 2. So remember, I like to work horizontally then vertically. That's just how I learned to do it. If you don't do it in this order, it's not necessarily wrong. It's just you have to make sure you get all of these facts in there. So I'm going vertical next. Vertically stretched by a factor of 2. There's no reflection there, so we just put 2e to the negative x plus 2. And finally, shifted up by 4 units, I add 4 at the end. So with all of that, I get the following set of graphs, color-coded. So here is our e to the x, our initial e to the x graph, right? Then e to the negative x is taking that and flipping it over, so it's this blue graph right here, e to the negative x. Then we shift up, we shift to the left by 1, so this green graph is just shifted this blue one to the left by 1. So e to the negative x plus 1. Then 2e to the negative x plus 1. Essentially, every value on this one is going to be stretched by a factor of 2. So it means everything is getting multiplied by 2. So if I have this value, I don't know exactly, it's not going to be a nice number, but here is something like 7.5. It should be something like 7.5 times 2 once we're done. So 7.5 times 2 is about 15, which, yeah, that's pretty much in line with that. So that makes sense. So we can see that that's approximately 2 times each of these y values. And then finally I take that purple graph and shift the whole thing up by 4. And so that shift up by 4 will actually change my horizontal asymptote. So I get a new horizontal asymptote at y equals 4. My y-intercept has been altered greatly here. So let's sort of track that y-intercept. The original one was at 0, 1. And remember, when we reflect over the y-axis, it doesn't change. But when I do my left shift, that point would change to negative 1, 1, right there. And we'd get a new y-intercept. So the new y-intercept is going to be 0, comma, e to the negative 1, which is not a nice number. 1 over e is a very ugly fraction that I can't do in my head. It's some decimal that is not going to be nice. But the point is it's no longer 0, 1. Then, once I multiply by 2, that's going to change it again. So this value here becomes negative 1, 2, because I multiplied the y value by 2. And the new y-intercept right there is going to become 0, 2e to the negative 1. And then finally, everything getting shifted up by 4, we get this point going up by 4 is going to be negative 1, 6. And the final y-intercept is 0, comma, 2e to the negative 1 plus 4, which is ae to the negative c plus d in this case, right? Which is what we expect our 0 to be, or our y-intercept to be at. So it all sort of tracks how you would expect it to be, and it's reflected in the graphs we've made. Now, what about if we start from having a graph? How do I identify what a graph is when I'm given it? So here, I want to know what the equation of this graph is. So I have f of x equals a times b to the x plus d is my basic form. Yes, I'm missing c, or the possibility of negative in front of the x, and all of that, but that's actually okay, because if we remember our exponent rules, let's think about this. B to the x plus c, that is equal to b to the x times b to the c using our exponent rules. Well, b to the c can just be contained within a, because b is a number, c is a number. So I can actually, when trying to solve for an equation, I don't need to think about what is c. I can just kind of house it within the a value. So we simplify it that way. Similarly, because b to the negative x just equals 1 over b to the x, I will house that possibility of a negative within my base. So the most basic form of an exponential that we would want to use to solve like what the equation of a graph is, we're just gonna not have c, and we're not gonna have any negative exponent here. We're just going to work with this because this gives us all the information we need. We can manipulate it later if we want to show some shift from some other value, etc. But in general, that's not really what we're looking for. So a times b to the x plus d. How do we find the equation? So first, I've already done this for us, but you would want to note a few points, at least 2. It's very helpful if you have the y-intercept especially. And you want to take note of what is the asymptote. So in this case, note that the asymptote always occurs at y equals d. Remember that up and down shift, the vertical shift, is the only time the asymptote changed. So this is a very easy one to tell what d is. We just look at the asymptote. So in this case, the asymptote is at y equals -1, so d is just automatically -1. So we're already 1/3 of the way there. Next, we want to look at the graph without its vertical shift. So basically, I'm going to take all of this and shift it back up by 1. So I'm going to take all of the points that I noted originally and just think about those, because you don't necessarily want to have to redraw the entire graph, but you want to think about, okay, if I shifted all those points up to where they need to be, or down if it was a different picture, so that they're back where they would have started from without that vertical shift, what would the y values be? That's what you want to think about. So here, once I've done that, I have my new points within my shifted graph, or my unshifted graph. We want to find 2 consecutive integers with points on the graph. So in this case, I have my y-intercept and 1, 6. And we're going to then find that b is equal to y2 over y1. Notice that I said consecutive integers. So it does matter that I picked 0 and 1. It doesn't have to be 0, 1. It could be 1, 2, 2, 3, 4, 5. It can be -1, 0, whatever we want, as long as they are consecutive. So I pick 0, 1, and then I take the y values. So 6 in this case, we have, this is y2. So if this is x2, y2, and this is x1, y1, we do this in order. 6 over 2 equals 3. That tells us what b is. You can check your work by doing this with 2 other points. So if I take 2 other consecutive points that I have here and say 2 over 0.667, or it's supposed to be 2/3, right? So this is 2 over 2/3, which should be 2 times 3 over 2. 2's cancel. That's 3. You should get the same thing. So you should be checking this with more than 1 point to make sure you're doing it correctly. Or more than 2 points, I should say. So 3, that's our value for b. So next, the y-intercept of our unshifted graph, that just tells us what a is going to be. So our y-intercept is 0, 2, so a is 2. And then we're done. So that's all we need to tell what this function is. There's really a lot less that goes into it than like polynomials where we had to solve for a using known points, etc. Here, the y-intercept just tells us what a is, as long as we have taken the step to unshift the graph. Remember that step, because you will get all of this wrong if you don't unshift it, so that the horizontal asymptote is where we want it to be. Alright, so with that said, we're just going to look at the first kinds of common exponential applied problems that we can run into. There's going to be a lot of application problems that we go over in this unit. Most of them will come a bit later, but these are a couple of the ones that we know that we can figure out how to do right now. So these are formulas you are going to need to know. First, the compound interest formula. So compound interest means interest on top of interest. So if I get 5% cash back, and then I get 5% on top of that 5% later, and like that's basically how most investment accounts work, where I get 5% interest, and so now I have $105, and then I get 5% interest on my $105, so I now have 100 and whatever that would be, etc. That's compound interest. It's compounding on top of itself. The formula to calculate compound interest is given here. So A of t equals P times 1 plus R over N to the NT, where A of t is the account value, T is pretty much always going to be measured in years, P is the starting amount in the account, often called the principal or present value, that's where the P comes from, but essentially it's the initial value in the account. R is the annual percentage rate, APR, which we express as a decimal, so it will be given to you as a percent. We will use the decimal form to plug into the equation. And then N is the number of compounding periods in 1 year. What is a compounding period, you may wonder? Essentially, the way compound interest works is interest is compounded at different times throughout a year. So, most, for example, savings accounts, you'll get compound interest monthly. So at the end of each month, they'll add interest onto your account. And then the next month, they'll add interest again. But notice that R is an annual percentage rate. Annual means yearly. So if they say, oh, your savings account gets 12% yearly, that means it gets 1% per month, essentially. So we need to divide that out and take into account, well, it's gaining 1% a month, but it is 1% on top of 1%, on top of 1%, on top of 1%, and so on. It'd be very nice if it was 12% yearly. Very rarely are you going to find a savings account that actually gives that amount, but I digress. So, essentially the words you want to recognize are going to be the following. In any compound interest problem, you're going to want to look out for these words. Annually means that the compounding period is once per year. Annual means yearly, so it's one time a year. So N would be 1. Semi-annually means twice per year, every 6 months, so N is 2. Quarterly means 4 times a year, so N is 4. Monthly means every month, so 12 times a year, N is 12, and daily is 365. So you really just want to look for these LY words within these compound interest problems to just tell you that's what N is. So in this example, we have invested $3,000 in an investment account paying 3% interest compounded quarterly. How much will the account be worth in 10 years? So our first step in any of these problems is to identify each of the variables that would apply to the equation. So we have $3,000, 3% interest, quarterly, 10 years. So $3,000 is our initial investment, so our principal, so that will give us P. 3% interest, that's our interest rate, our annual interest rate, which we will give as R, but remember that we are going to state it as its decimal form, so 0.03. Quarterly, that's going to tell us what N is. Quarterly means N equals 4. And finally, 10 years, T is measured in years, so this will be T. So in the end, we get each of these values, which we can then fairly easily plug into this equation. We just have to replace each of the parts. Like so. Now, here's the big thing that's a common problem in these chapters is, especially when working with exponents, make sure that you know how to plug this stuff into your calculator. Because if you get all of this, you'll get most of the credit on a problem. But there will still be points allotted to you getting your final answer. Please, 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 practice plugging this in, because with a lot of calculators, especially because you won't have a graphing calculator to work with necessarily, it can be kind of tricky to plug in these types of problems, making sure that you get the exponents right, etc. So practice it on your calculator. Make sure you can actually get $4,045.05. If you don't get that, talk to me. I can help you figure out your calculator, but I can't give you general information about calculator plugging in, etc., because every scientific calculator tends to do this differently, so I can't tell you what your calculator does unless I can see it. But please make sure you get this answer, that you practice plugging in. Similarly, the next formula, this one tends to be even harder to plug into calculators, even though it looks simpler. So practice this one too. Alright, continuous compound interest. This one looks more like our exponential equation. It's even got an E in it. So this is essentially continuous compound interest means we're taking n towards infinity. We are always compounding. So continuous means that at every moment of every day, we are compounding this interest, which feels a little weird. Like, how would that be possible? We are infinitely compounding it at all times. Well, because we know that there's this weird sort of limiting value that occurs when we take our values of an exponential out to infinity, etc. That's the definition of E. We actually get this formula. That's where E came from originally, was investigating a problem like this. So if I make n infinity, if I take both of these n's to infinity, what happens? E shows up. Again, not something you need to understand. A very, very smart mathematician came up with where this figured this out for us, so we don't need to. Though if you take calculus and beyond, you may eventually derive where did E come from. So for right now, though, we get this equation. A of t equals PE to the RT, often referred to as PERT. So A is still just the amount in the account after t years. P is still the principal, and R is still the percent rate, which we will express as a decimal. But notice that there is no N anymore. N was the compounding periods, and we can't put those in there because N is infinity. There's infinite number of compounding periods. So instead of n, we've got our e in here. But remember, e is a value, not a variable to plug in for. So e is just e. It's 2.718, etc. So if we invest $3,000 in an investment account, paying 3% interest compounded continuously this time, how much will the account be worth in 10 years? Notice that this is the same question as before. The only thing that's changed is instead of it saying quarterly, it's saying continuously. So for every other one of these frequencies, we would use the compound interest formula. But if it says continuously instead, we use the continuous compound interest formula. Alright, so compounded continuously, it's all the same information. We just don't have an n anymore. So I plug into my new equation. I get 3,000 for p, e to the 0.03 times 10. Once again, please practice in your calculator to make sure that you actually know how to get $4,049.58 out of this. Plugging in e to an exponent into scientific calculators can be very unintuitive. So practice this. I'm not kidding. Some calculators are very weird about this, so make sure you can figure this one out. And also, note, when the same investment was compounded quarterly, we only got $4,045.05. So notice that compounded continuously, we get more. This is another way you can check your work on a problem like this, is that if you have the same numbers for a compound interest problem, the more frequently you're getting interest, the more interest you should make. Even though all the other information is the same, the more often you're compounding your interest, the more money you'll have in the end. So if it's annually, you're going to make less money. Semi-annually, more than annually. quarterly more than semi-annually, monthly more than quarterly, continuously more than any of those. That's the most you could possibly make on an investment, is if it's compounded continuously. So if you're ever out there trying to invest your money, that's really what you want to look for, is things that allow for continuous compound interest. Though, again, finding a good investment like that is kind of hard sometimes. With that, we now have a good introduction to our exponentials. We'll be moving on to looking at logarithms next. But for now, if there is anything in here that you're really rusty on, make sure, please look at reviewing exponential rules. They're going to be very helpful and necessary to working with these types of problems, so make sure you know them.